Hey everybody, this is Lydia.
Hi, this is Avery.
Hey, it's Catherine.
Welcome to week 2 of PLIX CubeSats online. Some upcoming workshops, we'll be having PLIX community calls later in August, and then at the end of the summer, we'll be having a second round of PLIX Urban Ecology online. Also in the next couple of weeks, we will be establishing the calendar for our fall and winter online workshops, and we'll keep you posted. And you can RSVP to any workshops if you haven't yet through this link. The agenda for today, we're doing a little welcome right now. Avery is going to give a short presentation on testing subsystems and payloads in regards to CubeSats. And then we'll talk a bit about the activity for mission 2. We will break out into discussions like last week and come back together at the end and talk about what we talked about. It's going to be great.
Awesome. So welcome back, everybody, or welcome to new folks as well. As a reminder, this is the second in a series of 3 missions for PLIX CubeSats, with the ultimate goal of building out this model satellite and launching it on a tethered balloon. Today's mission focuses on satellite testing and payload integration. So this is taking your model to the next step, making sure it's structurally rigorous, and then integrating some functional payload in order to create or generate data with your model satellite. So the introductory discussion today will focus on just those topics: testing, the idea of subsystems, and also selecting payloads and what different payloads can do. But before we dive into that, I wanted to share out some examples from the making prompt that you're all able to post on the forum. And these examples, I think, demonstrate really good design or engineering practices or constraints that will be helpful to patrons as they carry out their 1U builds. And the first comes from Tina from the Queens Public Library. So Tina came up with this really clever way to rig up the balloon using rubber bands. And this is the exact way that you'd want to tie up your balloon or your satellite to the balloon. It's fixed on the center of gravity, and the payload itself is centered. It's fixed in place. So whatever functional payload you have is looking down towards the Earth in a fixed location. Eva and Kevin also had great examples demonstrating great insulary practices, so that insulation inside is protecting the FruitSat payload while maintaining a very lightweight balance of the CubeSat overall. So that balance between structurally rigorous, protective, but also maintaining that really light balance. So those were great to see. And Rachel and Alessandra also had great examples. Rachel used a foam material rather than cardboard to generate a sort of rounder configuration of a CubeSat, and also used a 3D printed creature as the payload. And so this hints at the idea of using a makerspace, maybe a 3D printer, other tools to not only create the CubeSat, but to also generate a payload inside. Alessandra's build hints at actually our discussion for today, which is the idea of subsystems. So in addition to the payload, which is the Clementine in this case, she's also included a battery and a microcontroller called a Bluebird. And all of these different components would interact somehow, ideally, in a CubeSat to carry out the mission design. And so all of these subsystems, or all of these elements, the battery, the microcontroller, the fruit, those are considered subsystems of the Cube satellite. So you've all built out these model satellites, and the next step would be to test them rigorously for something we call space qualification. And this is because you don't want to launch your satellite into space without having tested it. There are so many different environmental factors and stressors that are really going to put your CubeSat to the test. And so we, in advance of launch, carry out all of these rigorous testing practices to make sure that when it's up there, you know that it's structurally sound and all the electronics are going to function. And there's a couple of main components to this. So on the left, we see a rocket launch. So again, there's a lot of vibration that's occurred during rocket launch. And then in space, you're encountering extreme temperatures, both very hot, both very cold. Space is a vacuum. It's also very far away, so you have to make sure that you're able to communicate with your satellite and that you're able to power your satellite as well. So these are just some examples of testing. The first relates to mechanical testing, and the most common practice is to do vibrational testing. And so basically you just attach your satellite to this bed that shakes it rigorously in different directions, X, Y, and Z axis, and make sure that not only is the surrounding structure or the bus holding up, but that all the components inside are really locked in place really rigorously. This is another form of testing, which is meant to emulate when the different stages of a rocket come apart during launch. It's called pyroshocking. And this is basically, it's basically like hitting a hammer really hard next to the cube satellite and doing that same sort of thing, making sure that all the mechanical structure is in place, that it's not going to come apart when it experiences this massive shock. There's also environmental testing. So in addition to the physical stressors experienced by satellites, you also have to think about thermal and vacuum. Thermal because space is, again, very, very cold at some points when you're farther away from the sun. When you're very close to the sun, it's extremely hot. So before you launch your satellite, you do some thermal modeling to understand where the hottest parts of the satellite are going to be, and if this interferes with electronics in a new way. On the right, you see a thermal vacuum test, which is basically where you put your CubeSat in a massive oven, and you're able to emulate a vacuum condition of space. And throughout this process, you're actually powering your satellite. You're communicating with your satellite to see if all of the processes that you would expect to be required in space can actually function in this extremely stressful vacuum environment. There's also a really cool process called degaussing. And so basically any material that we interact with on Earth, especially metals, will have some sort of magnetic field. And this is something we don't want in outer space because we ultimately want to be at the mercy of Earth's magnetic fields. So you can engage in this process of degaussing, which removes any magnetic field from the materials from the Cube satellites, such that when you put it into space, it can actually, your Cube satellite can leverage the magnetic sphere of the Earth to orient itself into position. And that's sort of the final step related to space readiness. So subsystems. So you do all this testing ultimately to make sure that the series of interactive components or subsystems are working. So we discussed payload in the making prompts this week, and that is just one subsystem. And so these are some basic subsystems that you would include in almost every satellite mission. These include structure, so design of the actual vessel or bus that is housing all these different systems. You have to think about communication as a subsystem. So how are you uplinking information or commands and downlinking data and receiving that on Earth? You, of course, have to think about power. How are you giving power to your satellite? How are you carrying out these functions in a way that perhaps harvests solar energy in an efficient way and has enough to power your normal CubeSat operations? There's also something called attitude control. It's not altitude control, attitude control, which is this idea of sort of like we saw Tina's example, fixing the CubeSat in one location, the orientation of it, such that it's always pointing at something. If you want to look at a particular location on Earth, you have to make sure that you're using attitude control to look at a particular position on Earth. And same with if you're using a star tracker, you want to be fixed in position, fixed in attitude towards that star. There's also command and data handling. So you have to decide when, how frequently, and how much data you're going to be downlinking to Earth, because satellites create massive quantities of data. And storage can actually be pretty expensive, and the time used to get a ground station, which is the element that communicates with satellites, is actually pretty costly. So you have to think about that chain of command for data handling. And then finally, the payload. The payload is the subsystem that gives your CubeSat function. It is the biggest consideration for your mission design, and it is ultimately how you frame the other subsystems in terms of power, communication, and structure. You're all doing it around this one central payload. And these are just some basic subsystems. You can have more advanced subsystems like propulsion or navigation tracking. But in terms of a general mission design, these are the most commonly encountered subsystems. So just to quickly go over some imaging payloads or payloads in general, we know from last week from our mapping exercise that you can use satellites to take images. You can look at the development of cities. You can look at ocean color tracking. You can use visible cameras, you can use thermal cameras, basically many different ways to image using a camera payload. And on the right, you'll see that this is a very large camera. That's actually a 3U satellite. And this one camera alone is occupying almost 2 whole units. So that's 20 centimeters long of one cube satellite. So a very big camera. But you don't have to just take images. CubeSats do a lot of different things. So in terms of remote sensing, this is an example from a cube satellite that NASA built called RainCube. And this RainCube used sort of like echolocation to identify rainfall patterns using radar. So that's the payload on the left, a very big radar system. And on the right is the data output that we see. And this is actually the first instance of rain activity recorded in Mexico from outer space. So you're not just getting pictures, you can also generate sort of abstract graphs up for interpretation. Many different visuals come out of different cube satellites. Autonomous payloads. So payloads are also experimental. And this was a case, this IPEX satellite was a case of trying to determine in regard to the data downstreaming payload subsystem, how often to download data? How often should we be downlinking that data to a ground station? At what frequency? And specifically, the experiment was, can we use a software that is autonomous or that is self-aware to decide which images are worth sending back to Earth, or which data is worth sending back to Earth, and which is sort of just not worth the bandwidth of downloading. And so there's also just software-based payloads that that people are experimenting with. So all these different payloads can help inspire you for the second mission, which is testing and payload integration. This is like a much deeper dive than the first workshop. You're getting your hands a lot messier. There's a lot more experimentation in terms of payloads. And selecting a payload and integrating that payload, and a lot of sort of revision in terms of the engineering process and in terms of how you're going to fit your payload in, how you're going to alter the main internal structure to fit your payload, and ultimately how you'll complete your mission design as you launch your balloon. So sort of like the first activity, this mission includes an introductory discussion, so discussing the same sort of topics I had briefly mentioned before in terms of space environments and testing satellites. There's a main activity, which is selecting a payload and integrating it into the satellite. And then there's a come together discussion, which is how you chose to design your mission, how you chose or designed your experimental payload, and how exactly you plan to use it as you execute your final mission of launch. So in terms of mechanical testing, there's a couple of different things that you can do. So pretty much the easiest option is to just use a bunch of books to perform a compression test. And this is, again, just testing the mechanical structure of your satellite. Something that's really also helpful to have on hand is just a scale so that you can tell how much your satellite weighs, again, to achieve that balance of strength and weight, lightweight specifically. On the right is actually a shaker that is from a biology lab that we borrowed. And this was to emulate the vibrational testing. I don't expect everyone to have access to this, but there are some other ways that you can emulate this vibration testing. So in the activity write-up, you'll see that we wrote about attaching strings to either end and sort of pulling it taut to see if those vibrations are actually enough to test your satellite. And so these are just examples. You can also do things like a drop test. And I'd encourage you all to think of your own testing strategies, but more importantly, encourage patrons to come up with their own testing strategies, specifically perhaps related to their payload. So in regard to payloads, we put forth a couple of examples, all of different range of material costs and sort of difficulty or ease of use. And the first is space art. Space art specifically was inspired by the researcher from the MIT Media Lab Space Exploration Initiative, Annie Liu. And Annie Liu created this piece called Telepresent Drawings, where this was a payload sent into zero gravity on a Blue Origin rocket launch. And what she wanted to do is see basically the way that gravity was creating art, the way that gravity could paint in space. So she included this piece of graphite and this piece of paper and actually created a really beautiful drawing created in zero gravity. And so we use this as inspiration for our own space art creation. So it's pretty simple. You just use a piece of paper. You can use some any basically marking material. So we've experimented with paint, with crayons, with oil pastels, smashed up in all sorts of ways, thrown in various objects of different weights, and observed basically what comes out at the other end. And so this payload is in fact the lowest cost payload. It makes use of a lot of materials that are already on hand, and it's really great for engaging younger learners. And I'll also say that it's sort of the least technically rigorous. So it's a great way to start engaging with facilitation in terms of the CubeSat activity series. What's also nice about this payload is that patrons can experiment with different configurations in terms of material use, the way that they want to shape the paper inside of their CubeSat, the different objects they want to incorporate, and experiment with the different ranges of motion that will create different types of art observed. So it translates well in terms of doing a ground experimentation and then launching that on the balloon. It's also a great way to create a gallery, so you can either scan the images or you can post them in the library and create a beautiful gallery in your library space. Payload option number 2 are microbits. I'm sure that some of you have encountered microbits before, but these are microcontrollers that are sort of a nice introduction to more advanced tech tools or tech like a Raspberry Pi or an Arduino. In particular, because microbits harbor a number of onboard sensors. So the image on the left is this showing the gyroscope and also the accelerometer. So it can determine its directionality in the X, Y, and Z axes, but also can determine sort of how fast it's moving. There are other sensors also, including a light meter and a thermometer. So there's all sorts of different capabilities of it. And importantly, microbits can talk to other microbits, and you can set this up using block coding. And so what this means is that you can have one microbit in your satellite and one microbit on the ground, and you can use them as a system for relaying and receiving data, ultimately in a process that mimics that ground station satellite communication process. And so you can imagine that microbits, again, they're a little bit more advanced than the space art, but they're a good sort of gateway for engaging with microcontrollers. It does requires the purchase of 2 microbits, but microbits can be used for all sorts of different activities. There's also another PLIX activity that uses microbits to interact with Scratch. Another advantage is that microbits allow for real-time data collection. And so you can use all sorts of different softwares to do this, but it allows you to communicate and engage with the data in real time. And like I said before, it's a great way to introduce physical creative computing and the idea of microcontrollers as a sort of bridge to Raspberry Pis. And microbits are compatible with many different interfaces. So again, you can use Scratch, you can use something like MakeCode, but if you want to engage more advanced audiences or older learners, you can use a program called Mu to use Python. So a lot of range and dynamic range there. And the image on the right, I forgot to mention, is an example of a Scratch code that the PLIX team developed. Basically, that little character will move around depending on where the satellite is moving. So it's making use of that gyroscope sensor. Payload number 3 is a Raspberry Pi camera. This is the most advanced option, also the most costly, but also one of the coolest. And so the Raspberry Pi camera, in particular, the Noir camera, it is a type of camera that has an infrared filter removed. So you can actually do sort of quasi-infrared imaging. And what this means is basically just looking at the Earth in a little bit of different way. So on the left there, you'll see an example that we did of a playtest on the MIT campus. And importantly, this camera is super small. So you can see on the right there, it's about the size of a quarter and can use a USB battery. So it's a super lightweight option. You can also use other cameras, but because this camera is both lightweight and has that infrared capability, it's a great option to use. So again, this payload is best for engaging older learners. There's a little bit more sort of tech in terms of both setup and operation to use. But sympathetic to that, you can also dive into more complex topics. So you can think about visible or infrared imaging. And there's also a whole bunch of different analysis techniques that you can use. For example, NDVI, which is a way of looking at vegetative index or how much green space or how much vegetation is in a current area. It's also closest in mission design to an in-orbit cube satellite, given that you have this power source, you have the camera, you have to think about where you're imaging. So it most closely mimics that process of, building out a real satellite for launch. It's also a great way to generate data to interact with a lot of open source tools. So the image on the right is showing MapKnitter, which is an open source tool where people are crowdsourcing and contributing community garnered images, so that we have more active and dynamic maps over time. And so those are the 3 payloads. I'd encourage you all to think more about how we're going to be running these activities at a distance. So for example, creating make and take kits for each of the payloads, or experimenting with having patrons making videos or GIFs of different testing strategies. Or sort of like we did with the FruitSat. We sort of laid out a basic making prompt. There are many different remixes and interpretations of how exactly to build out that one FruitSat. So I think we'll head to the breakout sessions. I'm going to hand it off to Catherine now.
Yeah, great. Thanks, Avery. As many of you know, we're going to spend a little bit of time in breakouts now. They'll open up just below this window, and feel free to hop in anyone that has space. If you have any questions, just drop them in the chat, and we'll see you back here in about 20 minutes. Thanks.